Awesome. Thanks for having me here. I'm super excited to talk about this topic, something I've worked over this entire evolution at Replit. And this topic about how we are going from LLMs for just like writing code to actually these full-scale agents which can actually do end-to-end software engineering. And a lot of my work has actually been precisely this journey from training code completion models, which were state-of-the-art at the time at Replit, to actually now building agents for more than 20 million users. So I'm super excited to talk about this. So just quickly about Replit. Replit's a company based in the Bay Area. We're an online developer platform with a heavy focus on AI to help our users develop software. We have about 30 million plus users, more than 300 million projects, and more than 200 million tokens are generated daily. I think the number is about 400 million now, but as we move to agents and so on. So this is what Replit looks like, roughly. There are a bunch of moving parts here, but it's a full-scale IDE. You can see there's some code completion at the bottom left, which is a standard Copilot style ghost text completion. On the right, you have chat, which is this Copilot chat-like surface of asking questions, basically chat GPT within your IDE, asking questions, taking responses, applying them to your code base. And it has RAG inbuilt, so it has full structure of your code base with vector index, BM25, et cetera. You can see some inline actions, which is you highlight code and you actually have prompt well-engineered workflows to edit the code in the file. And then you also have this code repair thing, which is our agent. It's an autonomous agent built over an LLM, which just continuously keeps fixing like any static errors. So if you see those red squiggly lines, you have to not go and fix them on your own. It actually just does it. It's like autocorrect for code. So that's what Replit looks like. For today's talk, I want to focus on the key ideas behind this evolution from code LLMs to agents, rather than talking about specific results or papers or some of the stuff we are working on. The fact that this thing changes so quickly, I think the more important thing to focus on is like the key ideas and how is research moving along these axes, which actually is more informative. I will be skipping over some details here and there and some definitions, assuming people are familiar with the basic terms like LLMs, planning, and so on, but please feel free to raise a hand and I'll be happy to like detail the definition out. And then secondly, and this is the more fun part, I'll actually tell you my opinion on what comes next with agents. And I think a lot of the work which we're doing right now may be a local optima, and I'll try to prove that by showing how you can build something better and an example which we've been working on at Replit with some results. So moving on to the key ideas, this is roughly the framework in my head from this movement from LLMs to agents. You started with completion and infill. You moved to instruction, GPT instruct, and then chat. Chat GPT became a viral phenomena. You then moved to function calling, where you fundamentally made the LLM learn about how to use something outside just the document it's working with. So it needs to be able to make tool calls, function calls, API calls, and so on. You had code interpreter, which is, oh, now you actually write code, execute it, and you need to take the observations and that execution feedback back, and the model needs to be able to recognize and use it. And then finally, agents. So this is kind of like the timeline, the overall like guiding structure I have in my head. And then I'm going to talk about key ideas which fit within this structure. So we chop up any machine learning problem in these like axes like data, evals, what the model looks like, inference, and so on. A subset of these are these 8, which I've put on the slide. And I think they're interesting ideas here of how LLMs have moved from just being model-based, simple completion-style like systems to actually like full-scale agentic systems for software development specifically. And you'll notice the introduction of three categories, which usually we don't consider when we're training normal machine learning models. These categories of planning, memory, and this environment. And I would argue like these 3 are extremely critical and are actually core components to think about while you're building agents versus LLMs where you just thought about data, models, evaluation, inference. So jumping into the details a bit, let's talk about tasks and capabilities. So what is actually the difference between the capability of LLMs and agents, and how have tasks evolved over that? So with completion and infill, you just had next token prediction to next code block prediction. You had instruct chat, where you actually went from just completing the document to actually questions and answers, right? Chat required you to understand conversation trajectories, be able to refer to things back in the previous conversation history. Then you had tool calling, where now you actually have to generate structured function calls, which then will be interpreted, or like an API call, which would then be executed, and you would get results back. Code interpreter fundamentally required this capability to take execution feedback from your environment, and actually the model needs to be incorporated for its next sequence of predictions. And then lastly, agents have fundamentally, it's not about documents anymore, it's not about question answers anymore, it's not about chat conversations anymore, it's about actual trajectories over the entire application. And those trajectories are heavily influenced by planning, memory, reasoning, and actually the environment usage. So in summary, you go from documents to trajectories, you go from knowledge, models being heavily focused to be correct in terms of knowledge, to models being able to have higher accuracy about trajectories. You go from this working within a code file to actually working within an environment, and you go from narrow tasks to very open-ended multitask settings. One way I try to frame it, this task and capability shift, is this idea of if your evaluation has gone from human eval style evaluation, which was this canonical benchmark you see on the top right of just completing a code given a function spec, to actually a full trajectory or a project-based evaluation, which is given at the bottom. So you actually, for example, this is SweBench, which is the canonical benchmark for code agents these days. And it's about starting from a GitHub issue, generating plans, and then actually making a fix to fix that GitHub issue and generate unit tests to pass it. And roughly the big idea is you've gone from simple code execution to actually project and environment-based execution, and you're fundamentally now focusing on multiple tasks within that eval with a heavy focus on in-context learning. It's not about whether you know how to complete the function or whether you know Python syntax. It's about can you actually reason and in-context learn with the feedback from the environment to actually solve the task. So you have this now end-to-end evals like SweBench for agents, and then you also have some subtask evals such as Repo QA, which is, does your agent actually understand the structure of the code base? Can it answer long context reasoning based questions of the code base? So that's like roughly the situation of evals. You go from just code to actually full project based, and SweBench is the name you want to remember after this talk. The key idea which enables all of this is, of course, data. And the way I phrase it is you're lifting the shape and distribution of data. And so my claim is you go from code corpuses to then you reshape them to like these fill-in-the-middle style. You basically chop up your document into before and after parts to predict the middle. You then go to instruction response pairs. You go to conversation chains, and so on. But fundamentally, what is happening is you're always changing the shape of the data in the sense that you're going from just a document to pairs to actually trajectories which have multiple components, right? So it's instead of one column of text, for example, you're actually going to multiple columns of different things which you're then templating out into a context window. And the key thing is that in a trajectory, there are multiple sub-distributions. For example, there is a sub-distribution of how LSP errors occur, and then how do you fix them? There is a sub-distribution about how do you actually run a command to install packages for Python, and then incorporate that output after running the package install back into your thing. And this is the key thing, which is like the data has fundamentally changed in shape and distribution, and there is no way for agents to work successfully. You need this data, and GPT-4o and so on are actually have been trained on a lot of these this kind of data of trajectories. And the key engineering effort is actually just data engineering. So you have to be able to take data from all parts of your software development cycle, so your execution, your environment, your log traces, and so on, then actually build out your context to train the transformer on. You have to, one critical thing is usage of synthetic data. Traditionally, trajectory-like data does not exist in the world that easily. Only a few companies like Replit or like your telemetry of VS Code actually have that per action, right? So how do you actually go from this like corpus of data available on the internet to actually this trajectory-style data? And from our work and otherwise, synthetic data synthetic data pipelines are critical to this now. The key thing about synthetic data is like there are obviously concerns about mode collapse. But my particular way to think about is if you design synthetic data pipelines where the majority of the bits of information are actually coming from real world data, and you're just reformatting those bits of information or placing them together in logical sequences, you'll get less mode collapse versus trying to synthesize a full trajectory with an LLM. And that doesn't really work. And then lastly, because you can almost think like trust level FSD is like an agent, right? And the core thing behind that is like having a really good data flywheel. So you can tune your agent end to end. You can tune your trajectories end to end. So these are the things which are pretty important to think about data engineering when you prepare data sets from LLMs to agents. The next big thing is tools and environment. And so with an LLM, you just could output text in a code file, right? And then and work with it. But now with agents, you actually fundamentally need a suite of tools and an environment which the agent runs on, and then secondly, takes feedback from, right? So in agent parlance, we call tools and commands to actually to call interactions where the agent is doing something to the environment, and observations where the environment is surfacing some information to the agent. And one of the key ideas with agents for software engineering is that you have to have a very specific interface for these software development agents to interact with your computer. So like how humans use VS Code or use Bash and so on, that the SWE agent paper proves that it's actually is very suboptimal for LLMs to be coding agents. What you actually want is a very specifically custom designed interface, which these guys call the agent-computer interface. And that is built in a way so that LLMs are more effective at using it. So for example, human beings can use Vim, but LLMs, if they try to use Vim, they'll just get lost into trajectories of HJK and like trying to move around files. So that's like one way I represent that idea. And you can see that table on the right. That basically shows if you just have an LLM with RAG, you just have an LLM with just access to a shell, that actually has subpar performance compared to like an agent with compared to SWE agent, which is essentially where the key thing they're trying to demonstrate here is they have an ACI. Lastly, there is a huge shift in how we train models from pre-training to post-training. So pre-training used to consume the most amount of flops in GPT-3 era and so on. And now, fundamentally, post-training has been the biggest emphasis for most of the big labs. And you can see this with the kind of papers they're working on and so on. Despite that, I think pre-training is still a critical component. You need to have you need to have trajectories in your pre-training mixture. Otherwise, the latent shift from pre-training to just post-training is too large. If your model has never seen a trajectory, and if you just try to fine-tune it or do reward modeling of trajectories, it will have no idea. One very interesting development is tree search-like post-training. And so on the bottom right, there is this paper, Alpha LLM, which is basically get this loop of the LLM actually imagines potential solutions, it searches, and then criticizes. So post-training is it's absolutely critical for making agents work properly. The last is modeling. And the big idea is your models have to be larger. Your context windows have to be larger because agent trajectories are so long that your architecture fundamentally needs to be able to support long context windows. And the focus is a lot more on the agent architecture versus the model architecture. So you're less worried about how your layers are built and your blocks of layers are built in a transformer and so on, but actually how different modules, such as a memory retrieving thing, or like the LLM itself, is how they're composed with each other. So agent architecture over model architecture. And then lastly, one more thing, is memory. So short-term, long-term memory. LLMs traditionally just have context window as memory, but agents need to have long-term memory, which is what humans call experience, for example. And this is fundamentally to tackle ideas of lack of infinite context. If you had infinite context with perfect retrieval, you could probably just use a full context window. Memory also lends to planning because you need to be able to remember things to be you need to be able to remember where you're at in the trajectory to actually plan effectively. And planning is roughly some kind of structure which needs to guide your trajectory for the task. And you need to remember that structure, which is important. If it's just one shot, then it doesn't really work. You need to be able to say, this is where I'm in the trajectory. I need to come back up or not. And so the analogy I have is like a computer's memory stack. Your program goes to different stack frames, comes back up, goes down, comes back up. And on the right, for example, you see this one paradigm of planning, which is adapt, is like, oh, if I fail, then I want to generate a new plan, try to solve that sub-problem, and then come back. And so there are a couple of limitations with SWE agent, which the SWE agent paper says, which is the canonical reference. So editing has been very, very difficult for agents. And so they get, once they start actually, basically, once they start failing, they cannot come back from it, which is what the charts at the bottom show. And most of these failures are actually edit failures where they actually get the implementation wrong, are not able to make the edit correctly, or fix it if they get feedback from the LSP, for example, and so on. And errors just keep cascading. And these are some personal observations from just building agents in practice. So retrieval and needle in the haystack are these very common things, and you'll see these nice plots where people say, oh, we have perfect needle in the haystack. But these things are completely different from being able to do long context reasoning. Long context retrieval is unequal to long context reasoning. The second big thing is there's an extremely large variance in trajectory steps, even if you try to control for temperature. And so for the same case, you run one trajectory 10 times, and you'll get drastically different results. And you have to really tune sources of variance, which is like sequence of step calls and so on. One thing I think people forget is function calling and tool usage are huge bottlenecks for code specifically. So your function call distribution, like if you try to output a large chunk of code as an arg in an OpenAI function call, it actually does really poorly. It might be able to do it for like structured schema and so on, but for code specifically, it doesn't work. The data distribution doesn't match. Of course, there are hallucinations. Environment and runtimes are very painful to set up. Python installation has always been a pain for most of us. And like imagine that if you start expanding that to like C++ programs and so on. And the big thing is errors compound. LLMs fundamentally have this problem. If they get one token wrong, they start compounding this epsilon, which is what Jan LeCun talks about, and that's why he's completely bearish on LLMs. And you see that not just at the model, but you also see at the agent, which is like they get steps wrong, and they keep compounding error. And it's extremely expensive to get an iteration loop going. Like the full SWE bench, which is roughly about 2,600 samples, is like more than 6K to run. So even Replit as a startup has to be very careful about how to actually iterate. So you just can't keep going back and forth, and try to like just make the number go up because it's too expensive. So coming to the next part, this is slightly shorter, and more than happy to answer any questions on this, but I'll give you a view on what I think is next based on some observations and just working and trying to build these LLMs for the last year or so, build these agents for the last year or so. So I think currently we are in this paradigm of using LLMs and agents by like this coercion of like prompt engineering and siphoning information back from your environment to the context window. Like you're basically always converting this information into a prompt or text, which matches the data distribution of what the LLM sees and make it work. But I would claim that where the future is headed in terms of these agents, especially for software development, is like you have these native large action models. So suddenly they're not language models, but they're actually modeling out actions, states, and IDs. And let me describe that a bit more. So your models are effectively not trained on corpuses of text or text response pairs or like trajectories and so on, but they're actually trained on packets of information of the IDE itself. I'll explain how that works in a bit. And that, I think, is strictly better than trying to use agentic frameworks like React or like ACIs, the SWE agent ACI idea, and trying to coerce LLMs to actually work as an agent by just prompting. And the insight is basically, as we saw with the progression from completions to agents, there is this fundamental idea of lifting your data distribution, which is going on. You go from the code file to actually like instruction response to like using the environment through tools to actually trajectories. But I think what you really want to do it is you want to even lift it one step higher and actually make the data be equivalent to everything which your IDE does. So it's like every keystroke typed in your IDE, every event which happens in your IDE, LSP event, debugger event, and so on. And what that kind of looks like is at the top, you have this stream of events, states, and actions which are going on in your IDE. So you type some code, that's an event. There is an LSP error which triggers, that's a state. You run your code in the IDE, that's an action. And you have this stream of these packets in this session, right? And within these, you have these windows of tasks, right? Some sequence of These packets are basically you trying to configure your environment. Some sequence of these packets are you trying to configure your fixing error, right? And what you really want to take is those packets of information and then fine-tune and give your model the ability to say, given these states, events, what are the actions that are going to happen? Or given what these events and actions, what is the next state I'm going to achieve? And so what that looks like in practice in an LLM modeling paradigm is you actually take this stream, you actually build out these packets within well-defined tokens. So you have specific tokens trying to represent a category of information, and then you put relevant information in that. So for example, if you have an LSP error, you say LSP error token open, you actually put the error in, LSP error close, and so on. So that's one way you can tokenize, which is similar to the current LLM tokenization paradigm to get this data out. And I'll try to give an example, a very narrow example of what does building something like this look in practice. And the main motivation to do so is because Replit has this kind of data, these kinds of data sets are not available. So I want to shed some light into actually what actually goes on, how to build these things. I'm going to go over it quickly. I didn't get enough permission to share everything that I wanted to, but I'll be more than happy to answer any question. So the core thing we're building is Replit Code Repair, which is an autonomous system which every time it automatically detects whenever you have an LSP error and then fixes it. And so the problem at Replit is we get more than 150 million LSP events a day. And that's why it's important to make it autonomous in fixing. And a lot of them are beginner programmers and so on. So if you can actually even save 1 second per programmer, you're actually achieving a lot of productivity. And let me see if I can get a video working, maybe not. So that screenshot is basically what it looks like. So you're just continuously typing, and whenever it sees an error, it will just suggest this thing, and you can accept it. And if you even enable it saying automatic application, it'll keep applying it. So think about it, your iPhone autocorrect, right? You're typing code, and it keeps fixing it. It keeps fixing it. We've tried to build it in a way which is actually this native typing experience because it's autonomous. You don't have to be prompted every time, oh, hey, do you want this thing? Do you want this thing? Do you want this thing? No, it actually fixes it while maintaining a full context of your code base. One data point I can share that is we have more than 60%, just application rates. So more than 60% of the users, when the agent autonomously applies, they fix. They accept it. They don't say, oh, this is bad, or they try to revert it with an undo action. So that's an interesting data point. For context, Copilot's completion rates are roughly around 30 to 40%. So just that number seems promising enough that maybe this is a step in a good direction in terms of product experience. And so our approach is basically we have this Replit's end-to-end session data, if you remember the thing I talked about. So we have every single state, event, and action from the ID because we control the entire stack, all the way up from the network call to actually the button being clicked on Replit to run. The second important thing is using synthetic data over this session data to actually build proper, clean, high-quality data sets. Third is this, then you take that data set and actually template it out in a way where you can train it in an LLM paradigm, so you actually tokenize them into packets and so on. And then lastly, you just deploy them. And this is roughly what the data looks like. So in code IDEs, the unit of information of any edit in your file is called an operational transform, which is it's a keystroke. Or you inserted this character, you skipped this character, or you deleted this character. And so it's basically just JSON blobs of one of these three transforms which happen, and then you compose. Google Docs also uses the same thing behind the scenes to actually track what you're editing and what other people are editing. We have all these session events, such as an LSP diagnostic in this case, or a run event, or a debugger event, and so on. And then of course, we have the file system, which is what is a code-based state given each of these actions. So using these three units of information, you can actually build a full view of going back and forth for the entire project. And that's exactly trajectory-like kind of data which you want to be able to train agents. I want to spend a little bit of time on just synthetic data. And so this diagram is just a simple way to say that you actually have to build these complicated synthetic data pipelines, taking real-world data to actually template it out. So for example, for our case, we actually take the raw data, run it through an LLM to get the final Y label, check it with our actual file system, verify it again with an LLM as a judge because you want to reduce noise as much as possible, and then you do all the post-filtering of duplication and so on. But essentially the message I'm trying to communicate is like it takes a complex synthetic data pipeline to go from like raw session data to actual trainable, useful data, because the data doesn't exist in that format in the first place. And this is honestly the hardest part of a project when you're trying to build action models. And I'm trying to give a picture of what that looks like. So for example, what we're taking is if we have code, we put it into a packet of information in the context between these code tags. We have an LSP error, and we put it between special tokens of LSP error. We have an error, and then the error line the LSP error is occurring on, you can put it into tokens. And if you think about this, this actually mirrors the idea of function calling and so on, right? Where you're actually using these special tokens to indicate, hey, I want the LLM, this is not just text, it's actually moving into a different domain, and it can be parsed out from the context and actually used. So this idea of using special tokens to actually denote packets of information will be critical, I think, and I think we're already seeing that expand more and more. For example, Anthropic's Claude 3.5, one of the core things they do is they have this special ant thinking token. So in the UX, you actually don't see whether they're actually whether doing this chain of thought, but behind the scenes, the LLM actually predicts ant thinking, a chain of thought, closed ant thinking, and then because it's so well-defined, they don't show it in the IDE. So that's just a case in point of like how these special tokens will actually be used to augment the LLM's ability from just like predicting over like corpuses to actually being able to like work with an environment or be useful in other ways. And so these are some results. I have a blog post with a lot more detailed analysis of the results. Just for the sake of time, I wanted to like demonstrate the idea, hey, we can even take a 7 billion model, train it in this way, and fine-tune it in this way, where we can match GPT-4's performance out of the box with all the prompting techniques with it. So the key thing is like, okay, you can train small models effectively on these kind of trajectories. That means your 7 billion parameter models can actually model out these kind of like trajectory use cases, in this case of code repair. And it's an example of existence for being able to train models with this session-like, large action model-like paradigm I was arguing for with for code bases. So that's the big picture of like how to work with this data and actually train these large action models. And I think more companies and more products can be built in software engineering and otherwise if you try to take this paradigm. Everybody thinks, okay, how are you going to compete with OpenAI if they have all the data and so on and if they're best models, but actually they don't have some sub-distributions of data of these actions. And I think that's a very interesting opportunity, both in the software engineering space, and I think it's a glimpse into what comes into the future with these big models. Thanks for listening. I'm happy to answer any questions or go into anything in detail.
Hey, thanks, Madhav. Great presentation. Over here.
Yeah.
One quick question. The trajectory data issues that you mentioned, is it faced by code LLM, or it's like a common issues with all the other types of LLM?
So I think it's a common issue with all kinds of LLMs. So even you have these web agents, which actually works on trajectories of how to use the browser. And these issues of trajectory failures, of not being able to recover from trajectories and so on, are more a consequence of how we model rather than just the use case distribution. So the answer is yes. I think you were going to see that in most places. Sorry? Yeah. We definitely see that. And then you have to always keep fine-tuning with the data wheel to actually tackle these issues. That's why the data flywheel starts becoming very important.
Hello. Question about the code editing and like syntax fixing thing. Do you use a lot of synthetic data there, where I assume that like one of the reasons why language models aren't very good at doing things like syntax fixing or editing things that you specify is because it doesn't have data to be trained on that. And I would imagine this would be a really easy low-hanging thing for synthetic data, where you have a correct implementation of something, you then mess it up, and then you've got the fix for the mess up and everything. Is that something that happens in that code editing training?
For sure, yeah. So there are two specific ways the data set is constructed. One is exactly what you're saying. You take code which is working and you perturb it, right, with an LLM, right? Yeah. And so now you have your X and Y pairs very clearly. The second, which also in our experience works if you do enough denoising, is basically actually take the raw problem, which is like the erroneous code and the error, and then you make the LLM fix it out of the box. So your 80% of the bits in that, for example, prediction are coming from the real world, but the LLM does have some idea of like what good code looks like in this context, and it's able to do it. So TLDR, we go both ways.
And just to follow up, one of the things that you said about model collapse and everything, how does that translate into the domain of coding where we have a very well-defined environment as opposed to model collapse when it's usually referred to in like natural language, for example?
Yes. So, so two observations there. I wish I had an ablation to point to, but one is the space of code outputs is smaller than language outputs. So for 1,000 tokens, you have a lot more ways to put English in rather than code, right? Syntactically correct code. So that does accelerate model collapse, like mode collapse quite a bit. And secondly is I think you have to control the distribution very carefully across even basic things like, this different programming languages, but also different code lengths and so on. So TLDR, mode collapse is easier to run into with code, but it's also easier to solve because you have like some kind of way to filter out things much more cleanly than English.
All right, we're out of time, but you guys can come up and bombard Madhav with questions. That's very welcome. But we have another session starting at 4:20.
Yeah, thank you so much. Thank you.